In this module, you will learn about binary operations. In earlier classes, you learned that the solution to almost all mathematical problems involve some arithmetic operations like addition, subtraction, multiplication and division in one way or another. These operations involve two quantities and yield a single quantity. Hence, these are also called binary operations, as binary means two. Binary operations can also be defined in terms of functions. Let A be any arbitrary set. A binary operation star on a set A is a function star from the Cartesian product of A to A. We denote star of A comma B by A star B. Let us consider an example to take a broader view. Let Q denote the set of rational numbers. Let A and B be any two rational numbers. Now, on adding, subtracting and multiplying any two rational numbers, we get another rational number. Hence, the function addition from Q cross Q to Q, defined by plus of A comma B is equal to A plus B, is a binary operation. Similarly, the functions subtraction and multiplication from Q cross Q to Q are also binary operations. Now, the division of two rational numbers may not result in a rational number, as A divided by B is defined only when B is not equal to 0, otherwise it is not defined. It means that division from Q cross Q to Q is not a function, and hence not a binary operation. Therefore, we can conclude that addition, subtraction and multiplication are binary operations on Q, but division is not a binary operation on Q. This result can be extended to the set of real numbers R. Also, do check it out. Consider a finite set A with the elements 5, 6, 7 and 8. Let $ be a relation from A cross A to A, defined by $ of A comma B is equal to maximum of A comma B. Here the maximum of any two elements of A also belong to set A. This shows that $ is a function on A, and hence a binary operation on A. This binary operation can be expressed using the table as shown. Here, we have 4 rows and 4 columns in the operation table, with the ijth entry of the table being the maximum of the ith and the jth elements of set A. Such a table is called an operation table. In other words, when the number of elements in a set A is small, the binary operation $ on set A can be expressed with the help of a table called the operation table. In general, we can say that if A is any finite set with n elements, and star is a binary operation defined on A, then the operation table will have n rows and n columns, with the ijth entry being AI star AJ. Conversely, given an operation table with n rows and n columns, and each entry being an element of the finite set A, a binary operation on A can be defined such that AI star AJ is the entry in the ith row and the jth column of the operation table. The number of binary operations on a set A is equal to the number of elements in set A whole raised to the power of the number of elements in the Cartesian product of A. For example, the number of binary operations on a set with 2 elements is 2 raised to the power of 4, which is equal to 16. This is because the number of elements in the Cartesian product of a set with 2 elements is given by 2 into 2, that is 4. Therefore, we have 2 raised to the power of 4. Let's again go back to set Q of rational numbers. Let A and B be any 2 rational numbers. Now, on adding A and B in any order, the result remains the same. That is, A plus B is always equal to B plus A. This implies that set Q of rational numbers is commutative under addition. Hence, the function addition from Q cross Q to Q, defined by plus of A comma B is equal to A plus B, is a binary operation. This discussion leads us to a definition. A binary operation star on set A is called commutative if x star y is equal to y star x for every x and y belonging to the set A. Hence, the function addition from Q cross Q to Q, defined by plus of A comma B is equal to A plus B, is a commutative binary operation. Similarly, the operation multiplication from Q cross Q to Q is also a commutative binary operation, since A into B is equal to B into A. However, subtraction and division are not commutative binary operations, as A minus B may not be equal to B minus A. And similarly, A upon B may not be equal to B upon A. For example, 1 upon 2 minus 2 upon 3 is not equal to 2 upon 3 minus 1 upon 2. Also, 1 upon 2 divided by 2 upon 3 is not equal to 2 upon 3 divided by 1 upon 2. Now, what if we have to associate 3 elements of a set under a binary operation star? In such situations, 2 cases arise. The first is that we can associate the first 2 terms and then associate the result to the third term. The second case is that we can associate the last 2 terms and then associate the result to the first term. If the result in both the cases is equal, then star is said to be an associative binary operation. In other words, a binary operation star on set A is said to be associative if A star B star of C is equal to A star of B star C for all A, B and C belonging to A. Now, addition and multiplication are associative on set Q of rational numbers. Hence, addition and multiplication are associative binary operations on Q. However, subtraction and division are not associative on the set of rational numbers, and hence are not associative binary operations. Now, let us learn something more interesting. On adding 0 to any rational number a, we get a. Hence, 0 is the identity for the addition operation for the set of rational numbers. If we define a binary operation addition on the set of rational numbers, then 0 is the identity for addition for set Q of rational numbers. Also, on multiplying any rational number a by 1, we get a. Hence, we can say that 1 is the identity for multiplication for the set of rational numbers. Therefore, we can say that 1 is the identity for multiplication on set Q of rational numbers. Mathematically, an identity for a binary operation star on A is an element E in set A such that A star E is equal to E star A is equal to A for all A in set A. Now, what if we get an identity on associating two elements of set A under the operation star? The answer leads us to a definition. Given a binary operation star on A with the identity element E in A, an element A belonging to set A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to B star A is equal to E, where B is called the inverse of A and is denoted by A raised to the power of -1. If we again consider the addition operation on Q, then -A is the inverse of A for the binary operation plus on Q. This is because A plus of -A is equal to -A plus A is equal to 0, which is the identity for the addition operation on Q. Similarly, if we consider the multiplication operation on Q, then 1 upon A is the multiplicative inverse of A for the binary operation into on Q. This is because A into 1 upon A is equal to 1 upon A into A is equal to 1, which is the identity for the multiplication operation on Q.